Did you know that a satellite or a space telescope can turn by any amount about any axis in space without using any external force, without any thrusters? It can do that. How? By using a principle called conservation of angular momentum. But what exactly is this? Let's find out. Let's start with something that we already know. We know that if an object of mass m has some velocity v, it has momentum, which is the product of mass and velocity. Why do we care about this thing called as momentum? Well, that's because if you have a bunch of particles, not just one, but a bunch of them, and if the total external force on that system of particles is zero, then the momentum of the system, which is basically the sum of individual momenta, that stays a constant. It doesn't change. And we call this the principle of conservation of linear momentum. And this is a super powerful tool in making predictions. For example, imagine a situation in which a block is coming with some velocity and hits another block, and let's say after the collision, they stick together and they move together. We want to find what that final velocity is. Well, if we consider both m1 and m2 as our system, and if we ignore friction and air resistance, then during the collision, the forces are all internal. There are no external forces. Then we can say momentum before, the total momentum of the system before the collision should equal the total momentum of the system after the collision. And just from this, in a couple of steps, we can figure out what that final velocity should be. Isn't this awesome? Why does it work out this way? Well, that's because if there are no external forces acting on the system, then during the collision, when m1 puts a force on m2, m2 puts an equal but opposite force back on m1. So whatever momentum has gained by m2, the same amount of momentum must be lost by m1. And so the total momentum does not change. Well, now you might say in real life cases, external forces are not zero. You have friction, you have air resistance, right? Yeah, but if this was a situation just before the collision and this is a situation just after the collision, then during the collision, the internal forces are much higher compared to the external ones. And so we can ignore them. We can pretty much say that, hey, momentum changes mostly happen due to the internal forces. And so we can pretty much use this principle and make pretty accurate predictions. Okay, now guess what? If a rigid body is spinning, then we know it has angular momentum, which is given as the product of its rotational inertia and angular velocity. And many experiments show for a bunch of rigid bodies, if the net external torque on it is zero, then the angular momentum of the entire system, which is again basically the sum of individual angular momenta, that stays a constant. So now we have something called the conservation of angular momentum. The idea is very, very similar to over here, except that this will be used for rotation. So let's take a few examples. Let's say we have a disk that is spinning on a frictionless table, and let the angular velocity be omega 1. Now let's say we drop another disk. This is not initially rotating, okay? We're gonna drop it on this one, and there is friction between these two. So this is spinning, this is not. What happens when you drop this on this one? Well, because there is friction between these two, the big disk is going to put a torque on the smaller one, trying to make it spin in this direction. But of course, this small disk will put an equal but an opposite torque on the bigger disk, slowing it down. Eventually, they will have the same angular velocity, and when that happens, the torque disappears, and now they will be both spinning together with the same angular velocity. And notice, if I consider both the disk as part of my system, there are no external torques, and therefore the total angular momentum of the system must stay conserved. So look, just with this principle, I can now predict what that final angular velocity is going to be. I can say that, hey, the total angular momentum of my system before, which is just rotational inertia I1 of this disk times its angular velocity omega 1. And what's the direction? Well, remember, for angular momentum, we can use our right-hand thumb rule. Our 4 curling fingers curl in the direction of the angular velocity, then the thumb points in the direction of the angular momentum. So over here, the angular momentum is just upwards, okay? Plus the angular momentum of this one, which is just 0, I2 times 0. That should equal the final angular momentum, which is going to be the total rotational inertia, which is just I1 plus I2 times the final angular velocity. And look, just from this, I can calculate what that final angular velocity is going to be. Isn't that amazing? Now, of course, one key thing over here is that the rotational inertia not only depends on the mass, but it also depends upon how that mass is distributed. If the mass is distributed farther away from the axis of rotation, the rotational inertia is higher. So the distribution of mass also matters. For example, for a disk, the rotational inertia is given as half mr square, where m is the mass of the disk and r is the radius. So we could plug that in and simplify, but you get the point, so we'll not do that. Okay, let's take another example. Consider spinning tires of an automobile. Imagine the car is jacked up, so the tires are not touching the ground. So the ground is not exerting any force or torque on these tires. Right now, the clutch is not engaged. So the two tires can spin independently because they're not connected. So let's say they're spinning with two different angular velocities, omega 1 and omega 2. Okay. Now, what will happen if I engage the clutch? Well, now these two axles are connected and they are now forced to spin with one particular angular velocity. So now they will have some new angular velocity omega. If we ignore friction and if we ignore the mass of the clutch over here and all of that, can you predict what that final angular velocity should be? Assume that the rotational inertia of this wheel is I1 and that of this wheel is I2. It'll be a great idea to pause the video and see if you can use the conservation of angular momentum to predict what that final angular velocity should be. All right, we're going to consider the two wheels as the part of our system. We're going to ignore the mass of the axles and the clutch and everything, okay? So what's the total initial angular momentum? Well, it's going to be the angular momentum of this wheel, which is just I1 times omega 1. And we have to be careful about the direction. In this particular case, the angular momentum of this wheel is going to be to the right. And this wheel also has the angular momentum in the same direction, so I can add it. So plus I2 omega 2. That should equal the total final angular momentum. And the total final angular momentum would be just, I1 plus I2 times omega. And boom, from this, I can calculate what omega should be. Of course, you could say that, hey, the two wheels are identical, so I1 should be equal to I2. And, we can further simplify this, but you get the point. Okay, now consider a box floating in outer space with a spinning disk inside of it. The disk is connected to a motor and the motor is powered by a battery. So everything, the disk, the motor, and the battery, all of it is completely inside the box. But because of the spinning disk, the entire, box disk system has some angular momentum, right? But there are no external torques on this system. So this angular momentum of this system must stay constant, right? Okay, so now imagine we could remotely control the motor and change the speed of the spinning disk. What do you think would happen if we reduced its speed? Well, the angular momentum of the disk would decrease, but the total angular momentum must stay the same. So how will nature ensure that? The answer is that the box itself will begin to rotate in the same direction. That way, the decrease in the disk's angular momentum is compensated by an equal increase in the box's angular momentum, keeping the total unchanged. So look, simply by slowing down the disk, we can make the entire box start rotating. No external forks or torques needed. Pretty cool, right? Now, what do you think will happen if we speed the disk back up to its original speed? Well, now the angular momentum of the disk returns to its original value, so the box will stop rotating, again to keep the total angular momentum the same as before. Finally, what if we increase the disk speed? Well, that would try to increase the total angular momentum, so to compensate, the box would start rotating in the opposite direction, again ensuring the overall angular momentum remains the same. Which means just by increasing or decreasing the speed of a spinning disk, we can rotate this box by any amount in any direction. This device is called a reaction wheel. And this is how we control rotations of satellites. So here's an example of how these reaction wheels look like. We have 3 reaction wheels to control rotations along 3 axes. And we usually have another set as a backup, just in case some of the others stop working. So this is how, by using the reaction wheels, we can rotate our satellites or our telescopes by any amount along any particular axis. Pretty awesome, right? What's more awesome is that conservation of angular momentum can also be applied to non-rigid bodies. Take a look at this. You have an ice skater who starts out spinning with low speed, but then look, she starts speeding up. Can you pause the video and think about what's going on over here? See if you can explain this using the idea of the conservation of angular momentum. All right, let's see. When she starts spinning, look at how her arms and legs are stretched out. Because of this, a lot of particles are far away from the axis of rotation, distributed far away from the axis of rotation. As a result, her rotational inertia is pretty high. She also has some angular velocity, and therefore she has some angular momentum, which is the product of these two. Now, as she continues to spin, we will see that she will pull her arms and legs closer. As a result, a lot of particles now are distributed close to the axis of rotation. Therefore, her rotational inertia goes down. But what happens to her angular momentum? It has to stay the same. Why? Well, because all the pulling forces were internal, so all of those torques are internal, and there are no external torques over here. I mean, of course, there is force of friction, but that is very minimal. So the torque produced by the friction is very minimal. So if I consider this ice skater as our system, then there are pretty much no external torque acting on her. And so her total angular momentum must stay the same as she pulls her arms and legs closer, which means this product should stay the same, which means as her rotational inertia decreases, her angular velocity should increase to keep the product the same. And that's why she speeds up. Let's have a look now. Here we go. This is what's happening. Isn't that amazing? Wow. And something very similar happens to the stars. A star usually forms with huge swirling, clouds of gas gravitating together. Now, if you consider this entire cloud as our system, then particles are distributed very far away from the axis of rotation. It's all spread out, so it has a very high rotational inertia. And it also has some angular velocity, and so it has some angular momentum, which is the product of these two. But when eventually a star is formed, look, almost all these particles are now distributed much closer than before, so the rotational inertia is much lower than before. But the angular momentum must stay the same because pretty much no external torque acts on our system. And therefore, the product should stay the same. And so the angular velocity of the star must be much higher than it was before, such that the product stays the same. That's why the star will be spinning faster than before. And when big stars run out of fuel to sustain nuclear fusion at the core, gravity crushes the whole thing into a very tiny, very compact object called neutron stars. As a result, the rotational inertia becomes incredibly low. But again, the angular momentum must stay pretty much the same as before, and therefore its angular velocity will be much, much higher so that the product stays the same. Now, this is not to scale. Just to give you some feeling for numbers, stars usually finish one rotation in like a few days, but these neutron stars will rotate tens or even hundreds of times per second. So now you can see why. It's all because of conservation of angular momentum. By the way, before we close, did you know how we actually discovered these? Some of them actually shoot out beams of electromagnetic radiation from their magnetic poles. And as the star spins, those beams sweep across the space like, a cosmic lighthouse, if you may. And about 60 years ago, astronomers noticed incredibly regular radio pulses arriving from deep space. It was about 1.3 seconds apart. And so the signal was so precise and it was so regular that at first they thought it couldn't be natural at all. Some even wondered if it might be intelligent alien life signaling us. So the mysterious source was labeled LGM1 for little green men until we found more of them and then finally realized that they were actually rapidly spinning neutron stars.